Some dates are just different. They almost feel like they have this weird gravity to them, pulling brilliant minds right into their orbit. And today, we're going to do a deep dive into one of those really remarkable dates. April 26. I mean, on the surface, it's just another day on the calendar, right? But in the world of mathematics, it's one of the most significant dates in history. So why? Well, it's a story of how our modern world was kind of secretly built, piece by piece, on this one single day across the centuries. Yeah, on this one date, in totally different years and different countries, four brilliant minds were wrestling with problems that define our lives today. I'm talking about everything from our politics to our health, from the art we see to the very nature of numbers themselves. So let's meet them, one by one. All right, let's start with a big one. Seriously, how do you take a country with millions and millions of people in different states and decide how many representatives each one gets? And more importantly, how do you make that system fair? Not just for right now, but every single time the population changes. Well, the answer, or at least the one the United States has been using for over 80 years, it goes all the way back to April 26, 1874, and the birth of a mathematician named Edward Huntington. See, Huntington looked right past all the messy politics and saw what it really was: a pure mathematical puzzle. So he developed what we now call the Huntington-Hill method, which is this clear, logical formula for apportionment. And how effective was it? Get this, it was adopted into U.S. law way back in 1941, and it's still the method used after every single census to decide the balance of power in Congress. To this day. It's just such a powerful reminder, isn't it, that what we often see as pure politics, the fight for representation, can sometimes be so elegantly solved by math. It's literally a formula for fairness. Okay, so that's our first genius of April 26th. Let's stick with the same date, but let's jump forward a couple of decades to a completely different problem, one that really affects every single one of us. So, how do diseases spread? It feels like total chaos, right? Just unpredictable and terrifying. But is it really? Or is there maybe a hidden pattern? Some kind of mathematical logic that could help us predict the path of a pandemic? To answer that, we have to turn to William Kermack, born on, yep, you guessed it, April 26, 1898. He looked at the absolute chaos of an epidemic and just asked, can I write down its rules? And Kermack's story is it's absolutely incredible. He started his career as a chemist, working hands-on in a lab. But then a devastating explosion in 1924, it took his sight completely. So barred from the physical experiments he used to do, he pivoted. He turned the full force of his amazing intellect to the world of pure theory. And it was there, working with A.G. McKendrick, that he co-developed the foundational Kermack-McKendrick model. It's this set of equations that reveals the hidden logic of how a disease actually moves through a population. What's so powerful about his work is that it gave us a way to see order in the middle of all that chaos. Think about it, a mathematical map for a biological storm. And his work, it is still the foundation of modern epidemiology today. All right, 2 down, same date, different year. Let's move to our next stop on this April 26 timeline, and you'll see how this builds to something even more abstract. But man, is it just as beautiful. Okay, I want you to think about those intricate, repeating patterns you see everywhere in nature, like in a seashell or a fractal, or even in complex art, like an M.C. Escher print. How does math even begin to capture the essence of something that repeats perfectly, infinitely? So, this time, we're going to look at the other side of the coin. It's not a birth, but a death. On April 26, 1902, the world lost Lazarus Fuchs, a mathematician who basically gave us a whole new language to describe this exact kind of infinite symmetry. Fuchs, he was working on these incredibly complex things called differential equations. And hidden deep inside that work was this new class of functions with these amazing properties of symmetry and repetition. I mean, his ideas were so profound that they directly inspired one of the greatest mathematicians of all time, Henri Poincaré. Poincaré took Fuchs's concepts and built an entire field around them, even naming them Fuchsian functions and Fuchsian groups in his honor. That's how big a deal this was. So look, while Fuchs might not be a household name, his ideas gave mathematicians a brand new toolkit to understand a really special kind of infinity, one that ends up shaping everything from theoretical physics to computer graphics today. So there you have it. One date, 3 amazing stories. But we've got one more genius to meet. This is our final stop on April 26th. And this one takes us into the purest, most mysterious corner of mathematics, the world of numbers themselves.
Let me ask you a simple question. How many ways can you make change for $1? Sounds easy enough, right? But what about for $100 or 1,000? This is the problem of what we call integer partitions, just breaking a number down into smaller whole numbers. And believe me, it gets impossibly complex really, really fast.
The person who saw the deep, hidden beauty in this exact problem was the legend himself, Srinivasa Ramanujan, an almost completely self-taught genius who tragically died on, you guessed it, April 26, 1920. Ramanujan's story is it's off the charts. With almost no formal training, he basically rediscovered a whole century of mathematics all on his own, and then went on to make these breathtaking new discoveries. And working with his collaborator, G.H. Hardy, he tackled that partition problem head-on. Together, they developed a formula so precise, so otherworldly, it could predict the number of partitions for huge numbers with just astonishing accuracy.
I mean, his intuition was the stuff of legend. It was as if he could just see the answers, like he was pulling these profound truths from a place that nobody else could even access.
And there we go. 4 mathematicians, all connected by one single day, April 26th. We've got Huntington, Kermack, Fuchs, and Ramanujan. So what's the real connection here, beyond just sharing a date on the calendar? What's the thread that ties them all together? Well, each of them, in their own totally unique way, stared right into a world that seemed messy or chaotic or just impossibly complex. And they all asked the same simple question: what is the pattern hiding inside of all this? And their answers gave us the tools to run our democracies, to fight pandemics, to create art, and to understand the very fabric of numbers themselves. It really makes you wonder, doesn't it, as you go about your day today, what unseen formulas, what hidden patterns are quietly shaping your world right now? If you look closely enough, you might just find them.